We've been talking a lot about how to compute derivatives, but what does the derivative actually mean? What does it mean? That's the topic of this lecture. It's called the interpretation of the derivative. And here it says f prime of a, which is the derivative of f with respect to x, evaluated at the point x equals a, is approximately equal to how much the independent variable will change if the dependent variable increases by 1, and that's at the instantaneous moment when the dependent variable is currently equal to a. Keep in mind that this is an instantaneous rate of change, so it's right at the point where x equals a. Okay, so on this board I've drawn a little picture of this. And hopefully you understand the difference between dependent variable. It's usually the x type of variable, but does not necessarily need to be called the letter x. And the independent variable is on what we usually call the y-axis, but again, this doesn't need to be y. Okay? So whatever's on this horizontal axis is dependent, vertical axis is independent. Here I've drawn in black some sort of function here, and I'm going to zoom in on the point where x is equal to a. This is the instant at which x is equal to a. If I was to draw this green tangent line right at that point and calculate the slope of that tangent line, that would be equal to the derivative of f of x evaluated at the point where x is equal to a. Okay? So when I say over here that this approximates how much the independent variable will change if the dependent variable increases by 1, I'm talking about the concept of the derivative being the value of the slope of a tangent line. Okay, because the slope of a line is equal to the amount of change in the y-type variable divided by the amount of change in the x-type variable. Right? So actually, if I step myself over by 1, the change in the x variable is 1, that's why I put the 1 down there. And then how much am I going to change in the f? Well, I'm going to go up, in this case, because the slope is positive, by about that much. Okay? So the actual value of the slope of the tangent line, if I go over by 1, if I run over by 1, it actually puts me at a rise right there. Now you can see that there's a slight difference between the dot on the green line and the corresponding dot on the black line right there. And what dot we have on the green line here is known as the linear approximation of f of x at the point A. You see, it's just off of f of a just by a tiny bit. The thing is, if we ever want to consider the quantity, which is like how much our y variable will change if our x variable goes over by 1, it might be easier for us to just take the derivative and evaluate the derivative at a given point, as opposed to having to evaluate both of these functions and then take a difference. Now when we get into a business application next, I think you'll see what I mean. Before I go on to that, I just want to discuss again that the units of the derivative, f prime of x, are always calculated as whatever the independent variable unit is divided by whatever the dependent variable is. Okay, so if we're going to talk about like the x variable being number of items sold and the y variable being cost in dollars, then it would be dollars per number of items sold. That's always how you do it. So as long as you can recognize the units on both the x and y type variables, then the units on the derivative are always the ratio of those two. Okay, so let's get into an example as it relates to business. Let's say I have a profit function. I've modeled my business with a profit function that describes to me the total profit I will make when I produce and sell X units. So P of X again representing total profit as it did in Math 147. That's all the profit I'm going to make if I produce X units. Okay? So let's say that this is my total profit function, and let's let X be in number of items that are produced and sold, and then P of X is going to be in dollars. Now I have the units on the y variable and the x variable, so you can take a guess, if I take the derivative of P with respect to X, what units will it be on the derivative? Yeah, it's going to be dollars per number of items sold. It's always like that. Okay. So before we actually start to calculate the derivative and interpret that, why don't we first go back to the average rate of change for a little bit of review. And that's because we're going to want to compare the average rate of change of this with comparison to the derivative. Alright, so let's give a couple intervals. What if I wanted to know what is the average rate of change of the y variable p of x, let's say over the interval from 500 to 1,000, and maybe over another one, over 1,000 to 2,000. Now from the previous lectures, you should definitely be able to give me values for this answer right here. If I gave you a function p of x and asked you what is the average rate of change of p of x over a given interval, you should be able to do that. So go ahead and practice doing that. And while you do that, over on this board, I'm going to draw a picture of p of x. And this is definitely something that you want to do when you're working by yourself. You're going to get to use your graphing calculator on all the tests in my classes, and you really want to have a picture. Once you get this answer, you'll see what I mean when I start to compare it with the picture. So not only should you try this right now, but also try to graph this function on your graphing calculator and change your window appropriately so you can get a good view of what I'm asking for here. Okay? So if you did that, hopefully you know that the domain is going to be x is 0 or greater. It doesn't make sense to have a negative number of items. And it looks like the y-intercept is at negative 100. And then we've got another intercept, a couple x-intercepts over there. And yeah, you should get something that looks approximately like that. Okay, so where are the numbers 500 and 1,000 on here? I think 500 lies around here, 1,000 lies around here, and 2,000 lies around here. So first what we should do is try to picture what are we actually asking for when we ask the question, what's the average rate of change over those two intervals? Okay, did you get those answers, those numbers yet? I'm going to show you how to calculate it right now. Alright, so let's talk about this interval in blue. What I'm asking for you in this question is to calculate this point right here, calculate that point right there, and then draw a line between them and calculate the slope of that secant line. Okay, so this is going to be a secant line that's connecting those 2 points. And, sorry, the m is equal to the slope of the secant line. Okay, and so what we need to do is just calculate what's the difference in the y's over the difference in the x's. And so you should have got that if you plug in 1,000 into this function, you get 19,900. And if you plug in 500 into the function, you should get 12,400. And then we would take that and divide that by the difference, how much we ran over here, which is 1,000 minus 500. And hopefully you got the number 15. Did you get the 15 there? Good. That's the answer to this question right here is 15. But if I'm asking it to you in context, I would also want to know what are the units on the 15? 15 what? And that's going to help with the topic of this lecture, which is interpretation. Okay, so 15 of, let's see, it's going to just be the y unit, which is dollars, divided by the x unit, which is item. Okay, so this is $15 per item. Okay, so what this says to me is that when I'm producing and selling 500 items, I'm going to make $12,400. When I'm producing 1,000, I'm going to make $19,900. So for every one more item that I produce in this interval, I'm going to make approximately $15 more for each item that I increase, okay? But it's approximate. Just like I was saying, if you're traveling in your car and it says that you made good time, you were going 50 miles an hour, you probably weren't going 50 miles an hour the whole time, right? Sometimes you're going faster, sometimes you're going slower. So that's going to be the point of the derivative versus the average rate of change, is that over here it says I'm going to make $15 for each additional item that I produce and sell, but it's not always going to be $15. Like maybe in this region it might be a little bit more, maybe in that region it might be a little bit less. All I'm saying is that if I took the average of all those rates, the average is 15. So I wonder if you also got the answer to this one here, because you can kind of see from this one why this might not be the most useful concept, taking an average over a large interval. Hopefully you got $0 per item here. 0? Maybe you got 0 and you thought, that's kind of weird, I'm not sure if that's the right answer. That's why I have a picture here, because if you know what to look for and you have a good picture, you can really check and understand if you have the right answer or not. Okay? So I'm asking in red for the rate of change between this point here and this point over here. And now you can see that when I'm producing 1,000, if I produce a little more, my profit's still going up. It's still going up a bunch more. But at some point, my profit starts to go down. And if I produce more, I'm actually going to get less money. And it turns out that 1,000 and 2,000 exactly hit on the same height. Okay? So the slope of this secant line M turns out to be 19,900 minus 19,900, and that's divided by 2,000 minus 1,000, and because we got the same y value on top, that's why we have $0 per item. So that tells me that if I'm thinking about a production level somewhere between 1,000 and 2,000, some might interpret this as, well, it doesn't matter because you're going to get the same either way. But it's not exactly true, because you see, if I'm at 1,000, if I move over a little bit, I'll actually make more money. But then at some point, if I move over even more, I'm going to make less money, and it just turns out that the average is $0 per item. Okay, so that's why these average rate of change aren't maybe as informative as an instantaneous rate of change, because when you're producing and selling certain items, you are at one current production level. The question is, if I want to move forward and produce one more thing or sell one more thing, am I going to make more money? Am I going to lose money? What's going to be the change if I increase by one? Okay, and that concept is what we've been calling our marginal quantities. So here for this, it's going to be marginal profit. Hopefully this sounds a little familiar from the previous class. We also had the marginal cost and the marginal revenue. Try to remember what those were right now. The marginal quantities were the amount of change in your total quantity if you increase the unit by one. And remember what I just had written on the board is the derivative is going to be an approximation of that. And that's the whole point of the calculus, is that we're going to take the marginal profit and we're going to approximate it with the derivative p prime of x. Okay, once again, the marginal quantities are the amount of change that you're going to get in your total quantity, in your y variable, when you change your x variable over and increase your number of items by 1. Alright, so we've already seen that that's approximately the derivative, which is to say that instead of kind of analyzing that, why don't we just take the derivative? P prime of x. Let's calculate the derivative, and then we'll compare that with some sort of average rate of change. Maybe we're going to do the average rate of change, let's say from 500 to 501. Okay, so while I'm writing this stuff on the board, I want you guys to use the rules that you've learned so far to please fill in what is the marginal profit. You may have heard of marginal profit in some of your other classes. It's a very common business concept, which is to say if I want to increase the x by 1, what's going to happen to my total quantity? So over here, I'm going to write down what's true, is that strictly the average rate of change of p of x over the interval from 500 to 501 is going to be the actual marginal profit at the quantity x is equal to 500. Okay, so actually calculating the average rate of change in the old way, where we did the slope of the secant line, which was a change in y over the change in x, that's actually what the marginal profit is defined as. It's how much it's going to change when you change your x variable by 1. But over here, I wrote that the marginal profit is approximately equal to the derivative. The thing about the derivative is it's easy for me to use my derivative rules. Here we're going to be using the power rule with the constant multiple and sum and difference rules. And we're going to take those and calculate the derivative, and then we can evaluate that for any number x we want. Like for example, if I want to calculate this, let's see how much work I have to do, and then we can compare it with this. Before we do that, did you guys get a functional form for this marginal profit derivative? Okay, so go to the derivative rules if you're still having trouble with that. You should get negative 0.02x plus 30, and the 100, the negative 100 just goes away. All constants just go to 0 when you take the derivative, okay? This one goes to 30, that goes to negative 0.02x. Alright, so let's calculate the marginal profit, the actual marginal profit, versus the marginal profit approximation, which is given to us by evaluating the derivative at that point. Okay, so here's our profit function again. And if I asked you for that actual marginal profit, what you're going to do now is you're going to find out what is P of 500, then you're going to find out what is P of 501, and then you're going to take the difference in the y's, okay? So that's the actual marginal profit. It's given to us by whatever P of 500 is, and that was 12,400. Oh, sorry, we have to do P of 501. So it's given to us by what is P of 501. So you plug in the number 501 up there, and P of 501 is 1,2,419.99. Okay, this is P of 501. Now I'm going to subtract away P of 500, which was the 12,400. And then I'm going to divide by the difference 501 minus 500, which is really equal to just dividing by 1 on the bottom. Okay, so the actual marginal profit I got is $19.99. And once again, it's really helpful for you to write down the unit. I cannot stress that enough. Whenever I assess you on paper, I will definitely ask you for the unit of the derivative and all the context problems. And the reason you want to put the unit down is because it helps you interpret the derivative. Okay? Remember, how much is the dollars going to change when the items goes up by 1? That's the pattern you always have. And so what it says is, if I'm currently at a production level of 500 units, if I increase production by 501, I'm going to make $19.99 more. Okay, so I'm going to make $19.99 off making that one extra item. Alright, so that was simple enough in practice. However, it did have a lot of steps. If you actually did this out, you notice you had to plug in 501 into that equation, plug in 500 into that equation, then take the then take the ratio. But instead of that, watch this. See how much easier it'll be for me to approximate this by just saying what is the derivative evaluated at the number 500. Okay, so instead of doing all that, what I'm saying is you could have actually just taken the number 500, which is the current production level, plugged it in right there, and you should have got $20 per item. And look how close that is to the $19.99, which is the actual marginal profit. The derivative serves as a very good approximation with $20 only being off by 1 cent. Okay, so why is this way better than calculating marginal profit in the traditional way? That really comes into play when I want to consider what my marginal profit will be for more than just 1 point. Like this was fine when it was equal to 500, but what if I want to know the marginal profit when x is 600 or 780 or 1230? I don't want to have to keep doing this over and over and over again. So if I just take the derivative once, I can evaluate it for any values of x. I can see all the values of x, and turns out that's really handy. Okay, so since it's so handy, because it's in equation form, let's do a little more, and let's graph the total profit and the marginal profit side by side. Okay, so here's the x again, here's the profit, and here's the profit function. And now let's graph that side by side with the same x. And what I'm going to do is graph the derivative. Actually, I'm going to graph it underneath so I can line them up. Okay, so that's the original profit function, and what I want to do underneath here is I want to make a graph of what the derivative p prime is, where p prime of x is equal to negative 0.02x plus 30. Okay, what does that look like? It seems like it's going to look like something like this. This is the graph of the derivative of p with respect to x. Okay? This is the total function here, and right here, this is a graph of the value of the derivative. Okay, so to put that into context of what we were talking about before, before we were saying when x is equal to 500 right here, what is the instantaneous rate of change? And if we looked at the tangent line, drew the tangent line right there, it's going up, and we calculated that the slope of this tangent line was $20 per item. That's the same thing as me saying, on this graph right here, where x is equal to 500, I have a y value of 20. Okay, so that's the graph of the derivative. It's really great that I was able to get this derivative in functional form because it allows me to analyze the way that this total quantity is changing for all the x at once. So I want to do a little bit of review for you right now. I would ask you, on what intervals is profit increasing and on what intervals is the profit decreasing? Okay, when is P of x increasing or going up, and when is it decreasing? Okay? This is something that you can answer by looking at this graph. This is also something to tie it in here that you can answer by looking at just the graph of the derivative. Do you remember how the words increasing and decreasing relate to the value, the sign of the derivative? Right? If your function's going up, then it means your derivative is positive. So that's why when we see the function going up from here to here, let's just call this point star right here, and it's from 0 to the star point. And then it's decreasing from the star point to, I guess, onward. It's always going to be decreasing after that because it seems like it's going down after that star point. So it looks like that star point's a pretty important point. Would you guys know how to find that star point already? Yeah, because this is a quadratic equation, right? So that's the vertex of the quadratic. So we could use a quadratic formula to figure out where the start point is. This looks like a very good point because at this point, my total profit is at its maximum. Okay? We would be able to use the vertex formula because it's a quadratic, but the power that calculus is going to give us in this class is that what if we have a cubic or a quartic, or what if we have an exponential equation? For those equations, you didn't get any vertex formula, okay? But what you're going to have is you're going to have the fact that at all the points where the function is at its highest or at its lowest, the derivative at that point is always equal to 0. So right here, the derivative p prime is equal to 0, okay? So another way to solve out for the special points where the function is at its highest or at its lowest is going to be to take the derivative in its functional form and then set it equal to 0. So I'd invite you to try that. You can find the vertex using the vertex formula here, and then try also setting this function equal to 0 and see if you get the same x value that locates the optimal value of the profit there. So that's really why the derivative is so powerful, because it will allow us to find those points. Before I end this video, I want to just show you how to interpret the derivative in the context of some of the other popular functions that you'll see in this class. Everything I just said that I did for the total profit is very analogous for the other total quantities, such as the total cost and the total revenue. And then we have another familiar pair of functions that we're going to be working with, which is the demand and supply equations. So I'm just going to tell you how you can interpret the derivative. What does a derivative mean in context if, for example, I've been given a demand equation like this. Demand equation is P is equal to minus 2Q plus 100. Remember what the demand and supply functions are? They're descriptions of what the market price should be set at given a quantity Q. This is the per item price that should be set at P. Okay? So what if I wanted to take the derivative of this function? Let's see if we could figure out what that would be and what it means. Let's see. So the derivative of P with respect, I want you guys to be taking this while I write this, please. The derivative of P with respect to Q, I'm writing it out in words because I want you to also be familiar with this notation. It's dP dQ, and that's the same thing as P prime of Q. Okay? Remember, there's two different notations. You might see it either way. This one's a little more helpful because it reminds you of what variable goes on the top and what variable goes on the bottom. In the same way, you can figure that out by this being the inner variable, the dependent variable, and this being the outer independent variable. And did you get what the derivative is? What's the derivative of P with respect to Q? Minus 2. That's right. So we're going to use a power rule here. This Q to the first power is going to turn into a minus Q, and then the constant 100 is just going to go away. Okay, so for this video, I would like you to now write a sentence of what that number minus 2 means. Like minus 2 what? So minus 2, let's see what's going to go on the top. Dollars per item demanded. Oh, price changes by. Okay, yeah, so the interpretation of the derivative in this context is that the top variable, the price, is going to change by negative 2. So it's going to go down by $2 for every additional item demanded. All right, so it's once you get the units on the derivative, it's pretty easy to get the interpretation out. Now what I want to do is show you this equation in another way, because you might not see it this way. You might have been given the same demand equation but solved for Q. Remember when we were talking about pricing, supply and demand, sometimes they were given both ways. So if I write down the same exact equation, so same equation, or negative P plus 2 plus 50, P over 2 plus 50, what if I gave it to you this way, and then I asked you for the derivative of that? Is that going to have the same derivative? Is it going to have the same meaning? What's going to happen there? Okay, so over here, Q was the independent variable. P was the dependent variable. That's why it was the derivative of P with respect to Q, dp dq. Let's do it again, but rewritten with P as the dependent variable, Q as the independent variable. Write down, similar to this, what the derivative would be, and try to write it out in words so you can understand. What is it going to be the derivative of now? Okay, so since I flipped it over there, it's going to now be the derivative of Q with respect to P. See, because now P is the input variable, Q is the output variable, so I have to switch it. Derivative of Q with respect to P, which is also called dq dp, right? Or I could call it Q prime of P. See how everything is switched depending on which one I want to call the dependent or independent variable? Alright, now let's try to calculate this. What is this value actually? Just like how that one over there was minus 2. What's this one going to be? Minus 1/2. That's right, because now I have to do the power rule on this, and you could see this as the constant minus 1/2 times P to the first power. So that's why I get minus 1/2 there. And so for the final bit of practice on this video, I want you to now write something here that's analogous to what it says here. Over here it says the price changes by minus $2 per item demanded. Now what's this minus 1/2? What is that saying? It says that the number of items demanded changes by minus 1/2 per dollar increase in price. Remember, the derivative is always going to be how much the y variable changes when the x variable goes up by 1. So, if I demand one more item, the price has to fall by $2. If I increase the price by $1, the demand is going to fall by 1/2 of an item. That kind of makes sense, right? That's saying the same thing, because then if I increase the price by $2, then the demand would go down by one item, and that's the same thing it says over here. The price decreased by $2 and demand go up by one item. Okay, so it's no coincidence that this derivative is the reciprocal of this derivative. It actually has to do with the properties of inverse functions, but we won't go into detail on that. The main thing I want you guys to take away from these two boards here is an understanding of what the derivative interprets to depending on what you're calling the dependent variable versus what you're calling the independent variable.